Circuit protection, terms and principles, part 2. Here we go. Right, we left off at the last one looking at discrimination. Let's dig into that a little bit deeper. What do we need to know about discrimination? Discrimination for short circuit faults. The total let through energy, so I squared T, it's current squared times time, of the minor fuse line must not exceed the pre-arcing I squared T of the major fuse link at the applied system voltage. Whew. If any of you know what that means, call me. No. So what we're saying here is that we talked about discrimination, and we said that the smallest device, or the closest to the fault, so furthest down the chain, is the one that must trip first. So the total energy, so our pre-arcing time of a fuse is the amount of time that after the fuse decides it wants it should be tripping before it actually starts to break down. So our total let through energy on the minor fuse line, so that's the closest to the fault or smaller fuse, must not exceed the pre-arcing energy of the major fuse link. So that means that the first fuse, the energy that it lets through before it's completely broken, before it completely breaks, must be less than the pre-arcing of the next fuse back, and any subsequent fuses back from that point. It's not the easiest concept to understand, but hey, it is what it is. So what do we got here? Fuse link 32, pre-arcing is, so this is our I squared T, current times time. Let's not get too fussy about what that means. What we need to worry about is the absolute numbers. So pre-arcing is 1050, total breakdown time at 415 volts, so that's our normal three-phase voltage, is 2,500, and then at 550 it's 3,660. It doesn't have a time. If we're at 80 amp, then it's 63,000. Never mind about any of that. So this is the amount, these ones here, total, these are the amount of energy that fuse is going to let through before it is completely, or the maximum amount of energy that fuse will let through before it is completely broken and completely open circuit. So this number here, if we're to get good discrimination, must be less than the pre-arcing number of the next fuse up. So if I had a 32 amp fuse, then and I was using it on a three-phase supply, so it's going to let through a maximum of 2,500 amp squared seconds. Can I use a 40 amp fuse behind that as backup? No, because by the time this one has blown, this one is starting to blow, and we don't want that. We want this one to not blow if this one can handle it. So this one here, the 50 amp, gives us a pre-arcing of 2,600, and therefore it falls within that. So I could use the 50 amp or anything higher as my next biggest fuse after the 32. Hopefully that makes sense to everybody. If you're struggling with that concept, let me know. And here we have a pretty little graph of total operating, total I squared T, and pre-arcing I squared T. There's our pre-arcing I squared T there, total operating there. These are different rated, stupid thing coming up at the bottom, different ratings of fuses. You can see these N1, 16 and 20. So what we're saying is that in order for one to back up the other, this total operating, the top of that square there, the top of that brown rectangle needs to be lower than the pre-arcing, the bottom of the next one, or whichever one we're using as backup. So could we use a 10? Could we use a 16 as a backup to a 10? Yep, because the 10 there, see the total operating, total I squared T is below that line, and for the 16, then the pre-arcing is above that line, so that's fine. And then we would have good discrimination. And again, what does discrimination mean? That means that the lower one will trip before the higher one. There's no point having the 10 amp circuit breaker on our lighting circuit if the 20 amp circuit breaker that powers our whole house just keeps tripping all the time. If the 20 amp trips before the 10 amp, then it's a waste of time to have both of them, right? Okay, discrimination for overcurrent faults. So that previous one is for short circuit faults, but for overcurrent faults, the time current characteristics of minor and major fuses, including their tolerances, do not overlap at any point. What does that mean? So remember, our time current characteristic means that as our current rises, our time taken to trip decreases. Now, if we have two fuses, one ahead of the other, and the time current characteristics overlap at any point, that means that at some point, as the current goes up, then the bigger fuse is going to trip before the smaller fuse, which again is pointless. We don't want that at all. We always want that smaller one to trip if possible. So let's have a look at the graph. What does that mean? So here's our time current characteristic for various different devices. Each one of these lines here represents a is it a circuit breaker or a fuse? I'm not sure. It doesn't matter. Let's say a circuit breaker. So this line here is a 2 amp circuit breaker. This line here is a 4 amp, 6 amps, 10 amps, 16 amps, 20 amps. So as this is our pre-arcing time in seconds, so that's our time, and then this bottom one is going to be our current. So as you can see there, that as the current increases as we go left to right, particularly around this area here, if we're looking at the 2 amp, then the total time for that device to break, or the pre-arcing time rather, goes down. And in fact, from here to say here, then that's a relatively small increase in current, but a large drop in time, right? So that's pretty good. That's a pretty good current characteristic or time characteristic curve. Should be pretty steep going downwards. If it's mostly horizontal, that means that with a large increase in current, we're not seeing much of a reduction in time. So more vertical is better than more horizontal in this case. Now, if this line here started to overlap any of these ones, let's say it took a sharp turn to the right and went down here, then that means if we had one of these larger devices protecting this smaller 2 amp one, then at this point here, then the 2 amp circuit breaker would fail to trip and the 4 amp circuit breaker would trip instead. That's if my 2 amp line started going this way, which is not right. We always want the 2 amp one to trip first. So what we want to see then is that those time current characteristics do not overlap, and this is in fact exactly what we have here. They do not overlap in any way at all. So that's good. Right, so that's it for discrimination. And look, it's a fairly large topic, and it's not easy. It's not obvious. It's not always the case of we'll just stick a smaller one in front of a bigger one. I've had situations where we've done that and still not had accurate discrimination. It can be a real pain in the butt. I had a situation where we had hanging PowerPoints, and where they attached to, there was a big bus bar on the roof, and where they attached in the roof, there were circuit breakers there, and they kept blowing, and of course that means that every time they blew, this is in a big workshop, every time they blew, somebody would have to come and reset them, either using a really big ladder, which is pretty dangerous, or getting a scissor lift in there, which is time consuming and expensive, just for resetting a circuit breaker. So what I had done was I had boxes manufactured that hung off the bottom of the cable. So instead of just a hanging PowerPoint, it had a box and it had the socket in there, but in that box was a circuit breaker as well, and that was a smaller circuit breaker than the one up top. That gave us some discrimination, which meant that if there was a fault on anything plugged into that socket, that hanging socket, it should trip the circuit breaker that was there instead of the one up on the ceiling, which means that we could just reset it then and there. And I want to say 75, maybe even as much as 90% of the time that worked, and we were able to just reset the breaker at that point rather than at the top. But it didn't work every time, and we still had to get a flippin' scissor lift in there. Seemed like every bloody week, but it probably wasn't. It's probably every couple of months to reset circuit breakers, which was a drama. So in that case, a better somebody had thought about it a little bit more before they did the installation, they would have realized that that was going to be an issue and done something about it. What could have our alternatives been? Maybe a higher breaker, a much bigger breaker at the top and a smaller one at the bottom to increase that distance, to give us a bit more discrimination. Maybe not putting circuit breakers at the top at all, although I have a feeling that when you're running off a bus bar system like that, it's actually legally required. I don't know. It was a hassle. It was a real hassle. Something to be aware of, and that's a issue that comes down directly and squarely into this idea of discrimination. Cool. All right, move on. What's our next thing? Rupturing or breaking capacity. Cool. This is a good one. So this is one, I think we've talked about this before, and for some reason it seemed to be something that was kind of hard for people to grasp, but to me this is very simple. It's the maximum current that a protective device can safely interrupt under fault conditions. So this is not about the rating of the circuit breaker. It's not about if you have a circuit breaker that's 20 amps, that's nothing to do with the rupturing or breaking capacity. This is the maximum amount of current that we can push through that circuit breaker and it will still trip. Remember that we talk about, like, if we put too much current through it, then the little contacts that are supposed to open when the circuit breaker trips might just weld together. If we get so much current through there so quickly and they just weld together, then the circuit breaker won't trip because it will physically be welded closed. So that's our breaking capacity or rupturing capacity. And remember, we talk about that in terms of our prospective short circuit current. So when we measure our short circuit current or our earth loop impedance, what we're doing there is trying to work out what's the highest current that will flow in the circuit if I make a short circuit here, and will my circuit breakers still operate correctly in that condition. Now, most of the time what we've found when we've done earth loop impedance testing and prospective short circuit current testing is that our prospective short circuit currents in P block on the fourth floor are something like 400 to 500 amps. And the typical breaking capacity of the circuit breakers installed in there is something around 6,000, and that's pretty standard. 6,000 is pretty normal. If you are in a situation where you need higher, then you go up to 10,000. I presume there's higher ones than that, but I don't think I've ever come across them. At some point you'd probably go to an HRC fuse, because HRC fuse is always going to have a greater breaking capacity than a circuit breaker, because there's no moving parts that have to separate. It'll just blow. It just blows that wire, remember. So in that case, look, we've got no problem. 6,000 amp breaking capacity, 500 amp prospective short circuit current, no problem at all. But it is something that we need to test. You will from time to time, if you're in a big factory that has really large supply cables, maybe even its own transformer, it's possible to get very, very high short circuit currents because they have very, very low loop impedance, right? It's a very, very low resistance between the switchboard or sockets or whatever going back to the source of supply, the transformer. And as that current goes down, the prospective short circuit current goes up. So we need to know what that short circuit current will be, and we need to make sure our breaking capacity of our circuit breakers is exceeding that short circuit current. There we go. There we have it. That breaking capacity must be greater than the fault current. Okay, and prospective short circuit current, I've just talked about that. We're talking about breaking capacity. That's the highest current possible at the point where the circuit is short circuited. So that's why we measure our earth loop impedance. What is the highest current that I could get in a short circuit situation? Backup protection prevents short circuit current damage to small overcurrent protective devices by wiring in series a fuse or circuit breaker with a higher breaking capacity. Okay. So I guess then you could say that if my circuit breaker had a 20 amp circuit breaker and it had a maximum breaking capacity of 6,000 amps, but I had a prospective short circuit current of 7,000 amps, well, what am I going to do? Well, if my backup protection, if my next fuse back in the circuit has a breaking capacity of 10,000 amps, well then that's going to be fine in that situation. That one will switch off. My main circuit breaker, well, my first short circuit breaker, the small one, might not trip, but the backup protection will. So at least then we should be safe. And there we have it there. There's a graph of the backup protection, right? So that as the motor starter overload relay, there is our amount of current So as the current increases, the time decreases. But then at some point that curve starts to flatten out, which means that as the current increases, the time's not going to come down very much at all. And then we have another fuse behind it that's going to take over, and that one will trip faster once we reach a higher current. Next one's close excess current protection. This is worth remembering, the difference between close and coarse excess current protection. We've talked about this before, right? That this a circuit breaker or fuse that will operate in four hours. It will operate within 4 hours at 1.5 times the designed load current of the circuit it protects. So if I have a 20 amp circuit breaker and I put 30 amps through it, as long as it trips within 4 hours, that is deemed to be close excess current protection. So that's the higher level of current protection. So that shows you that even at 1.5 times the rated current, so 30 amps on a 20 amp circuit breaker, it's often will not trip. It could take up to 4 hours to trip. Coarse excess current protection does not operate within 4 hours. So it takes longer than 4 hours at 1.5 times the designed current. So again, for a 20 amp breaker or 20 amp fuse, if I put 30 amps through that, then the coarse protection is going to take more than 4 hours to trip. More than 4 hours to trip. So that's the difference between close and coarse excess current protection. Just try your best to memorize those definitions. A utilization category is a combination of specified requirements related to the conditions in which the fuse link fulfills its purpose, selected to represent a characteristic group of applications, a term that replaced the concept of fusing factor. Let me read that again. A combination of specified requirements related to the conditions in which the fuse link fulfills its purpose, selected to represent a characteristic group of applications, a term that replaces the fuse factor. Look, that doesn't tell us what that means. It doesn't tell us what it means. It just says, well, there's some conditions that you need to know, and we talk about utilization category instead of fusing factor. Now, we've already gone through fusing factor, and the fusing factor is the one that you need to know for the test. So let's not worry too much about utilization characteristics. Right, merits of providing close excess current protection. So why would we provide close excess current protection instead of coarse excess current protection? Remembering, of course, that close means it will trip in 4 hours or less at 1.5 times the rated current. Coarse protection being more than 4 hours at 1.5 times the rated current. So the current regulations and standards require that cables be provided with close excess current protection, or the cable's current carrying capacity is subsequently derated, typically by a factor of 0.725. So what that's saying is that if we do not provide a cable with close excess current protection, close protection, then we have to derate the cable. Why? Because we're going to allow a pretty high overcurrent to flow through that cable for quite some time before the circuit breaker or fuse trips if we're using coarse protection. So now we have to use a bigger cable. We'll derate the cable by a factor of 0.725. Yeah, the effects of electrical faults. If we have a short circuit, we can have severe damage to electrical equipment. Great danger to life. For overcurrents, remembering an overcurrent is something that's higher than the rated current of that circuit, but it's not direct short circuit current. So this would be like 30 amps on a 20 amp circuit, or 50 amps on a 30 amp circuit or something. It's a danger of overcurrent, burnout of cables, and burnout of equipment, right? Because we get just that small amount of overcurrent over a long period of time could slowly deteriorate the cable or equipment. Leakage current, so this is where we get a small amount of current flowing to earth. And that we use an RCD protect us from leakage currents, right? So the effects of leakage current reduces the efficiency of a circuit because of energy loss. Because instead of all of the energy going through whatever it is that we're using, some of our energy is going just down to earth. So there's just a small amount of current flowing that we get no use out of. So then we're paying for energy that we're not using. And reduces safety factor and increases shock hazard, because if we've got a leakage current to earth, then we must also have voltage present upon our earth wire or on the earthed body of an appliance or a piece of equipment. So then there's a safety hazard there as well, because we've got some sort of voltage present. It might not be a high voltage, maybe it's a very low voltage in the case of a small leakage, a high resistance pathway to earth, but there's a potential shock hazard there because now we've got a voltage on the earth. And it creates earth leakage currents in the earthing system, which is not ideal, which means that we've got current running in our earth leakage system, or in our earthing system, which is not designed to be carrying current most of the time. Okay, that is the end of that. I will hold your attention for a moment longer and tell you that the second two digits of our code for this test are 18. So you'll have the first two digits from the previous video. Second two digits are 18. I'm just going to check that there's nothing in the test that we have not covered. Okay, we should be fine. Be aware, there were a couple of ASN ZS3000 definitions in this PowerPoint, and you're going to need to know those, or at least have them available for the test. I believe that all of the stuff in the test that's asking you to look at ASN ZS3000 is also in this PowerPoint. However, it may not be. If it is not, then you're going to need to find a copy of ASN ZS3000. We have links to those in various units all over the canvas, so I'm certain you'll be able to find those. As ever, if you need assistance, let me know. I'm here to help. See you next time.